Roots of polynomial functions. What do you do if you have like a degree 6 or a degree 7 polynomial and you're trying to solve it? We don't have factor patterns for a degree 6 or a degree 7. There aren't any. So you have to have a way to attack it and try to factor it out. Now, if you can just divide a few things out, hopefully what's left, you can then use your factoring patterns and actually get the beast factored. Speaking of which, I want to make sure that we write these two factor patterns down. They will crop up in this unit. A cubed plus b cubed factors into a plus b times a squared minus ab plus b squared. And then a cubed minus b cubed, the factor pattern is almost identical, but the negative moves. And it's an a minus b. Everything else is positive. A squared plus ab plus b squared. So I wanted to make sure that we had those in your notes so you remember them. Okay, so Roman number 1, the fundamental theorem of algebra. Fundamental theorem of algebra. Which is not actually as grandiose as it sounds, but it is helpful. The fundamental theorem of algebra. So the fundamental theorem says if you have a function f of x, and f of x has a degree of n, which is some number, then it has exactly n solutions or roots that are complex. Then it has exactly n solutions or roots that are complex. And by complex, we mean that this includes real roots and imaginary roots, rationals in both categories, and irrationals in both categories. So the total number of roots will be the same as the degree. One caveat is that roots with multiplicity, and now you know what that means, roots with multiplicity are counted separately. Roots with multiplicity are counted separately. So, for example, if you were factoring something and it was a degree 2, x minus 2, x minus 2, those would count as 2 roots using this theorem. So if there's duplicates, you got to count those duplicates separately. All right, so let's do an example. Let's say that f of x equals x to the 5th minus x to the 4th, and then it's got a whole bunch of other terms after that. And we want to know the number of solutions it has. Okay, so remember the degree when you're in standard form is the x with the highest power. So that would be the 5. So this is a degree 5 polynomial. And using the fundamental theorem of algebra, it means we're going to have 5 roots, which is the same thing as zeros, which is the same thing as solutions. So when you're done with the problem, count your solutions. You should have 5. Which is a nice way to check yourself. Okay, let's do another one. F of x equals x to the 4th minus 25, and we're going to solve this. Okay, so the highest power on x is a 4. So this is a degree 4 polynomial, which means we're looking for 4 solutions. Now we're going to actually solve this one because this is one that gave us a hard time on the test. There was one of the examples that had a factor like this one, and we did all kinds of really, really odd stuff. So if we're going to solve this, you set f of x equal to 0, and x to the 4th minus 25 is a difference of 2 squares. So it factors into x squared plus 5, x squared minus 5. And neither one of those is an a squared minus b squared. So that's as far as factoring is going to get us. So now we're going to solve. So we're going to set x squared plus 5 equal to 0. And we're going to set x squared minus 5 equals 0. Okay, so on the one on the left, we subtract 5 over to the right. So x squared equals negative 5. We're going to solve by extracting square roots. So 2 x's, and this is one where we just lost it. 2 x's, one comes out, but there's a positive x and a negative x. And if you don't draw the arrows, your brain will not memorize that fact, and you will only get one answer every time when there's 2. So the arrows help your brain with that. The negative under the radical becomes an I, so radical 5 with an I. And the one on the left, x equals radical 5i. The one on the right, when you multiply both sides by a negative, you get x equals negative radical 5i. So 2 rational, or sorry, these are, 2 irrational solutions. Okay, let's do the other one. This is the easy one. Add 5, x squared equals 5. Take square roots of both sides. 2 x's, one comes out. You have a positive x and a negative x. And square root 5 is as simplified as it gets. So x equals square root 5. When you multiply or divide both sides by a negative 1, you get x equals negative radical 5. The people that keep forgetting their 2 answers are the ones that aren't splitting it when they're doing their problems. And so your brain only sees the positive. Okay, but you'll notice degree 4, 4 solutions, 1, 2, 3, 4. You know you've got them all. All right, that's the short process for today's notes. Now we're going to actually do the long process. All right, Roman numeral 2, rational zeros theorem. Rational zeros theorem. Okay, so first thing you need to know is what the heck is a rational zero versus any other kind of zero, because you got to know what will this find and what will it not find. So basically a rational number is anything created from a fraction or anything that is a fraction. So like whole numbers like 2, I can put that over a 1. That's rational. 1/3 is rational because I can show it as a fraction. 0.12, a decimal that ends, is rational because I can show it as 12 over 100. I can show it as a fraction. So the fractions, all of the fractions you're going to be able to find are going to be real using this theorem. So now what will it not do? It will not give you radical zeros like the ones we just solved for, and it will not give you imaginary zeros like the ones we just solved for. So kind of the over strategy is use this theorem to divide out as many zeros as you can until you've got it down to something you can factor. And when you factor, that's when these will pop up at the end. Okay, so given polynomial, and this is the generic form of a polynomial, f of x equals a subscript n, x to the power of n, plus a subscript m minus 1, x to the power of n minus 1. And then depends on how many terms there are. The second to last term is a sub 1, x to the power of 1. And the last term is a sub 0, the number term or the constant term. And I don't expect you to memorize that formula. I just want you to have seen it before because it comes up with a lot of stuff we learn later and it refers to it. Okay, so given polynomial in that form, then, and here's the theorem, every rational 0 has the form, every rational 0 has the form P over Q, where P is a factor of the last term, which is the a sub 0 term, the number term typically, over a factor of the leading coefficient, which of course is attached to the leading term, which is our a sub n number. So if there are any rational zeros in this function, it will be one of that list. Downside, the list tends to be rather robust. All right, so let's do an example. F of x equals x cubed plus 2x squared minus 11x minus 12. Now, I'm very aware that a lot of the examples could be factored, but we're trying to take it easy on you as far as how long your list has to be. So you're still going to use the rational zeros theorem. Okay, so step number one is you're going to list factors of P. And the last term is P. It's a negative 12. So plus minus 1 plus minus 12. Now, all of these are going to be plus minus because a positive times a negative is a negative, and a negative times a positive is a negative. So everything's plus minus on your list. And then I've got 2 times 6, so plus minus 2 plus minus 6. And then I've got 3 and 4, plus minus 3 plus minus 4. Those are all the possible factors that could give us a negative 12. Okay, number 2, we're going to list factors of Q. Q is the invisible 1, the leading coefficient, which is nice because plus minus 1. And they're going to be nice to you. For most of the problems today are going to, the Q term will be 1, which will make your list a whole heck of a lot shorter. Okay, so number 3, we're going to create a possible zeros list. These are all the possibilities that could work. So P over Q equals, and if you have more than one term under the Q, you have to put each of these with each of the bottom terms. As it is, we only have one term down there. So 1 over 1 is 1, 12 over 1 is 12, 2 over 1 is 2, 6 over 1 is 6, 3 over 1 is 3, 4 over 1 is 4. Now, if there was like a 2 under there, I'd have to go 1 over 2, 12 over 2, which is 6. I have that. 2 over 2, which is 1. I have that. 6 over 2 is 3. I have that. 3 over 2 is 3 halves. Don't have that. 4 over 2 is 2. So you'd have to pair each of them with each term of Q. Makes a long list. All right. So this is our lovely list of possible rational zeros. So here is the guessing part. Don't you love guessing? We're going to test the zeros using the remainder theorem, which says if you direct substitute a number into the function, what it equals is the remainder. If it is equal to a 0, then it's a factor. Okay, so my favorites to start with are like 1 and negative 1 because they're easy. So I'm going to do f of 1. I'm going to direct substitute the 1 in. So I get 1 cubed plus 2 times 1 squared minus 11 times 1 minus 12. And then always do the power before you multiply. 1 cubed is 1, and then I'll do the power first. 1 squared is 1, then multiply by the 2. So plus 2 minus 11 minus 12. Now, you don't actually have to finish because you can tell this is not going to add up to 0. There's no way. It's going to be a big negative number. So once you know it's a no-go, you can stop. You do not have to completely calculate to whatever number it ends up being. All right, so now we're going to do f of -1. So -1 cubed plus 2 times -1 squared minus 11 times -1 minus 12. And do powers before you multiply. -1 cubed is -1. -1 squared is a +1 times 2 is 2. -11 times -1 is +11. And then minus 12. And this one actually does work. I get a remainder of 0. So we have a winner. Okay, now that you have your winner, you're ready for step 5. Divide out the 0. You can use synthetic or polylong. Most people do synthetic. So I'm going to put my -1 in the box. The coefficients are 1, 2, -11, -12. And there's nothing to fill. So we're going to do our synthetic. So bring down the 1. 1 times -1 is -1. Put it under the 2. 2 minus 1 is 1. Do it again. 1 times -1 is -1. Put it under the -11. Add them up. You get -12. Do it again. -12 times -1 is +12. And yes, we get our remainder of 0. So at this point, you should factor it and see if you can finish it on your own without having to find another rational 0. So I have an x plus 1 factor. I got that from the -1. And then from my synthetic, I've got x squared plus x minus 12 as what's left, which is actually factorable. So the last step is factor or find another p over q. Most of these you can just factor. We get x plus 1, x plus 4, x minus 3. And I'm going to skip the actual solving of these because I know you know how to do that. So my solutions are -1, -4, and 3. And we started with a degree 3 polynomial, so we know that we have all 3 solutions in front of us. All right, we're going to do one more example of this because I want you to have at least 2 examples in your notes. We're not going to write the steps out. We'll just do the problem. So f of x equals x to the 4th plus x cubed minus 2x squared minus 2x. Okay, using the fundamental theorem of algebra, this is a degree 4, which means we're going to have 4 solutions. We might only have 2 different numbers, but with their multiplicity, there will be 4. Okay, so when you start out, the one thing you can do to make your life a lot simpler is if you can divide a number or a letter to the front, do it. It'll make your numbers lower, easier to work with. So I can actually factor an x out of here, which gives me x cubed plus x squared minus 2x minus 2. So your p is the last number, which is now just a -2. Your q is the first number, which is the 1. And the reason that I'm using the inside and not the original is I've already factored an x out. It's this part that's left that I need to factor. So we're pulling out of the new equation that's left. Okay, here we go. P over Q. So -2 is plus minus 1 plus minus 2. A 1 on the bottom is a plus minus 1. Matching tops and bottoms together, I get plus and minus 1, plus and minus 2. So 4 possible rational zeros. All right, so now we're going to test them using remainder theorem. So f of 1 equals, let's see, 1 cubed plus 1 squared minus 2 times 1 minus 2, which 2 minus 4 is -2, so that's a no. All right, let's try the -1. So I'm going to have -1 cubed plus -1 squared minus 2 times -1 minus 2. -1 cubed to an odd power is a -1. -1 squared is a +1. -2 times -1 is a +2. And then I have a -2. And yes, this one is going to have a remainder of 0. So we have a winner. All right, so now that we know that -1 is a 0, let's divide it out. So put the -1 in the box. And then my coefficients are 1, 1, -2, and -2. And go ahead and do that synthetic. When you're done, write the factored form and look up to check your answer. Okay, so this one came up with a 0 in the middle. So it's like having a 0x term, but because it's a 0 term, you can disregard that. So right now we've got x times x plus 1 times x squared minus 2 equals 0. So that's as factored as it gets. So now we're going to set each factor equal to 0 and solve it. So x equals 0, x plus 1 equals 0, x squared minus 2 equals 0. So x equals 0 is your first solution. Subtract 1 to the right, you get x equals -1. We already knew that though, because we divided out using synthetic. Now, this is a degree 4, so we should get 2 solutions out of this for a total of 4. So we're going to add 2 to the right. X squared equals 2. Take a square root of both sides. 2 x's, 1 comes out. It's positive x and a negative x equals radical 2. So x equals radical 2 is another solution. And when you divide both sides by a -1, x equals negative radical 2 is our other solution. So we have our 4 solutions. None of them have multiplicity greater than 1. So 0, -1, radical 2, and negative radical 2. And I know some of the steps I'm showing you you're going to skip on your own work, and that's okay. I'm just showing you all the steps because it's notes, and I want to make sure we don't jump around. All right, are there any questions about this process?